So 1991st, here we go. I'll put those. All right, so for the first bit here, this basically wanted you to have a brief description on each of these statements and try to like showcase your knowledge of the differences between these strong and weak acids and how they behave in different solutions. So for A, it was asking about this diprotic acid. Why was Ka1 stronger than Ka2 or larger than Ka2? So this is as brief as I could probably make it. My other one is like a paragraph long. But basically the first dissociation of an H plus ion from hydrosulfuric acid occurs at a greater frequency compared to the second dissociation. So that greater frequency just means simply you make more ions. Make more ions, larger K value. That's just products of reactants again. And this is because it's more difficult to ionize an H plus from a negatively charged species because HS1 minus attracts the H plus through just opposites attracting. So it makes it difficult to rip off that extra H plus, which is going to be the second deprotonation step. So the attraction is going to basically cause a Ka2 to be lower. Simple as I can make it. Okay, I do want to show you, I'm bouncing, sorry. I do want to show you the reaction for that though. So we're basically talking about this first deprotonation step, donating H plus, making the ion in hydronium, versus what I'm speaking of for the second one is this ion, which has a strong attraction to its individual H plus, is less likely to give up its H2 water to make hydronium and then sulfide ion. So those are the two reactions that go along with what we're talking about. Thumbs up? Okay. And then the second question was, why is one labeled an acid and one's labeled a base? Basically in water, you're talking about Arrhenius' definition. And if you make hydroxide in water, you are considered a base by definition. And if you make hydronium in water, you're an acid by definition. So that was about as simple as you can make that one. And now I'm going to speak about bond theories a little bit more, but basically the H is coming off of this OCl, the hypochlorite ion, and we will talk more about, I saw some of you guys draw some pictures, and we'll talk more about OCl. The H is attached here. Basically the chlorine and the oxygen are both very electronegative, so they're pulling electrons this way, and so that weakens this bond. And that as you weaken this bond, it allows the H plus to kind of jump away and make it seem as if it's an acid, which it is. It's going to deprotonate. So that's what's happening here. This next question was asking about how HCl and HI, they're both strong acids in water, but when you put them in acetic acid, they behave a little differently. So my picture here is going to make more sense than I have it down here on the bottom. But essentially, as you talk about water, which has a bent structure, and those of you who are like, oh, I don't remember how to draw these loose spot structures, we have a whole unit on that coming up, probably in like 3 weeks, 2 weeks. So water, which looks like this, partial negative, partial positive, it's highly polar. So a polar molecule can attract other ions very, very easily. So as HCl is coming near it, the H is attracted, or the O of water is highly attracted to this H, and so it's very attractive and it will readily dissociate quite easily. But if you replace the chlorine with iodine, everybody, if you remember this, and if you don't, here's how you do it. Hold your fingers like this, 2 L's, okay? Turn your right hand to the left side of the room. Okay, your right hand represents atomic radius trends, and it's a very simple trend. As you increase, or as you go down a group, atoms get larger, and as you go from right to left, atoms get larger. It is a general trend. There's some little wonky moves throughout, but that's general. So chlorine is here, iodine is here. On your table, who's larger, chlorine or iodine? By far, it's vastly larger. It has like 2 more electron shells or clouds, so it makes it quite large. So if I replace this with iodine, it's huge. It's a large, large ion. So the positive nucleus and the electrons, which exist in electron cloud around it, cannot attract to its counter ion or its partner ion very well, because just simply this nucleus is so far away from the electron cloud of hydrogen, it just has a difficult time staying attracted. So water is like taking advantage of that. It's going to attract H+, and it will dissociate really, really easily. So basically water is able to do that with all strong acids, so in this case HCl and HI. But when you get acetic acid involved, it's not as polar. It is polar, but it's not as polar. So it can attract the H+ from a situation that's already not so stable, but it cannot really attract H+ from the HCl scenario, because this has a stronger attraction because they're both small ions. So they can kind of condense together a little bit more, and they have a greater attraction between the two simply because of the size of chlorine. This has a lesser attraction because the iodine is so large. So acetate can still cause dissociation from the HI situation, but not dissociation as well in a chloride, just simply based on atomic size. That's what all that says, basically. And then, what was the last one? Why is HF a weak? Yeah.
So all strong acids and bases are going to have like a larger attraction than their weaker acids and bases?
Actually, strong acids and bases actually have a weak, compared to weak acids and bases. Strong acids and bases have a weak attraction for each other, meaning they're two ions, which is why they dissociate 100%. They actually form ions. Weak acids and bases have a strong attraction, which is why they don't form ions very often. So that's like just the general rule between weak and strong. But if I'm comparing these two, they're both strong, but the question for this one was how do they behave in the presence of acetate? CH2, H3. So this one, acetic acid's a little less polar, so it just is not as nearly as capable as water in reference to dissociating these H pluses off with the presence of those strong acids.
Can you give like a general size statement? Which one did you say was?
Large ions dissociate easier in all situations. So large ion like iodine will dissociate easier in the presence of water, in the presence of acetate, in the presence of whatever. Smaller ions don't dissociate as well in all situations. But water does a pretty dang good job of dissociating everything, so that's why we compare usually a lot of things in the presence of water.
You pointed like the HI is like better dissociation than that. How about just like that strong acids dissociate?
Yeah.
100%?
So these, because they're all strong, all of our strong acids dissociate 100%. But if you just want an ion comparison, in the presence of water, both of these will dissociate 100% of the time. But in the presence of water, this one will dissociate probably, I'm sorry, not in the presence of water, in the presence of acetic acid, this one will dissociate probably close to 100%, calling it still strong. This one will probably not dissociate 100%, maybe like in the 90s or 80s, just because its smaller ion has a bit better attraction to itself. So water does a lot of the work. The acids don't really do anything. Water does most of the work. Any more questions on the size for now? Okay, we will talk about that more. This one basically compared strong acids to weak acids. I'm thinking, so HF, it was talking about being a weaker acid. Weak acids, HF, I don't have a picture of this one here. HF, does it have a strong or weak bond between the H and the F? This bond right here. Strong, so it does not dissociate well. So it's going to stay together, not make ions, meaning it's weak. Compared to HCl, this bond is what? Weaker, so it will dissociate into its two ions to make it seem as if it's a strong acid. So that's more compared to the strength of those bonds. So, oh no, I did want to stick here. Read this first. This is what I did not get to Friday. And some things are they counter each other. So it's not, there's not always a straight rule for everything, which is why I kept re-explaining some things differently. Read first and we'll talk. So in the first couple statements, talking about polarity of a bond, we will talk about electronegativity a lot more when we talk about our atomic trends, our periodic trends. But it's mentioning more along the lines of the strength of the bond and how that compares to the strength of the acid. So we know the stronger this bond here, the less likely the H is to pop off. So this would be considered a wet acid. A weak acid has a strong bond from its H to its whatever the rest of the ions are. And as you can go across the periodic table, carbon, nitrogen, oxygen, fluorine, as we go from carbon to fluorine, what's happening to, maybe you guys can remember this, what's happening to the electronegativity as we go this way? It's increasing, which is increasing the polarity of the bond. So that's the kind of the connection there. But it's saying that the binary strength increases as you go from here to here. So essentially what it's saying is the more polar bond basically means that it's going to break off its H plus easier, which is us saying it's a stronger acid. We know hydrofluoric acid is not a strong acid. Absolutely. It's a weak acid, but it's a stronger acid than water. Because water is amphoteric, can act as an acid or a base. And this is literally called hydrofluoric acid, which means it's acidic. So basically the bond, as it becomes polar, one side gets more partial negative, one side gets more partial positive. And if it gets so partial negative on one side, these two electrons that exist in the bond, because remember every bond contains two electrons, they basically just jump ship and they move over to the ion, to the fluoride in this case, and that would then release H plus to go cause some acidity in a solution. And then counter that, we go down a group, we know fluoric, bromic, and iodic. Which of these are strong acids? The last three. And then who is the strongest of those three in many situations, not just the water, but like the acetic acid situation we spoke of earlier? Say it again? Iodic is stronger because the ion size matters. So as we go from fluoric to bromic to iodic, the ionic size, fluorine, chlorine, bromine, and iodine is getting larger as you go down. And the larger the anion is, it's more likely to break off from its H plus, simply because of the lesser attraction it has. So those are your two statements you can use in terms of trying to explain why something's a stronger acid than another, or why something makes H pluses in solution and another one doesn't. But they're we are going to work with this some more just because they're wordy, and you can compare down and across, but you can't always compare like carbon to iodine. You can't always compare nitrogen to chlorine because they start to get mixed up in their trends. Give me a thumbs up when you're okay with that. So ion size matters. Okay. And then the last question was with KAs. I saw a lot of you guys attempted these quite well, so I'll let you check yourself at least. It would give you basically a titration. Sodium hydroxide neutralizes some acid. I don't know what that acid is right now. So in your neutralization process, it's diprotic, so you actually use 2 sodium hydroxides, make 2 waters, and NaC2H4.
That was oxalic acid.
Oxalic acid.
That's C3H4.
I mean, oh, it's oxalate. Oh, I wrote H. That's an O. Why did I write H? Because that's oxalate. Okay. Well, you know, H is an O, so there we go. Okay, so this is oxalic acid and sodium oxalate. But regardless, if you have a set amount of acid and you're trying to figure out how much base you need, you just need to use your mole ratios. So acid, mole ratio, 2-to-1 ratio, and then utilizing molarity as a conversion factor is very common for us to do, and it asks to solve for volume. So moles cancels with moles oxalic acid, and then compare that to the molarity of the sodium hydroxide, you should get 25 milliliters. So stoic. You okay with that? Yeah.
For RP, the overall, how do you see that? Is that given?
It's a possibility it was given. I'm going to say it had to have been given. Did it say K overall in there?
It was next to the reaction.
Next to the reaction. So it should have been next to this reaction, the full one. So essentially, if you have one reaction and you're solving for another reaction, the total reaction is equal to Ka times Ka1 times Ka2. So Ka1 times Ka2 is equal to overall. So just to modify, you just divide to solve for the one you don't know. And one thing you should notice is, how do you compare Ka1 to Ka2? Who's larger? Ka1, because the first dissociation always forms more ions than the second dissociation. And then, lastly, and then we leave in like 1 minute, so if you're going to pack up like a ninja. It asks for you to solve for the Kb from oxalate. So you back up to the last time you saw oxalate. You make it with water, or make it react with water. It has a single H plus donation. So this is referencing Ka2. So to backtrack to Kb, you do Kw divided by Ka2 and solve for just the Kb, basically how the ion is reacting as a base. Okay. So after for homework, finish lab, the tissue lab analysis conclusion, we have a couple questions there. There is an optional finale problem set, which is your like mixtures, weak acid, weak bases, strong acids, strong bases, salts of all different types. So if you don't feel good about what we did for warm-up, like basically have what we do in our lab, you need to do some extra practice. We have quiz this week. Okay, peace. I did not. I'm getting ready for honors, fam, you know.
Is it this tomorrow or is it sometime?
It's this week, yeah, it's not tomorrow.
This is the first part on this page.
Sorry, where's your I'm looking for the, let me see the 1990s. And then, I know your people. Here's, come this way for me. Oh, I also need to stop the video. Where am I looking? 19, thank you. It's easier for me to see from when you pointing out. You're good. Thanks, darling. Thanks. Figured you guys could find it faster than me. I was looking.